Okay, here are some solutions to the simple harmonic motion homework problems. Let's start with the first one. So you're given the position versus time for the oscillating particle. I'm assuming it's something like a mass on a spring. And you're told the mass as well, right here. The first question is, what's the period of the particle's oscillation? This can be answered by knowing the fact that position versus time functions for simple harmonic motion are usually written in the form of x equals a times the cosine of omega t, and possibly plus phi. This phi over here, right here, is called the phase angle, which for the purpose of this question is not important. But it's the omega that we're interested in. And so that is this piece right here. Omega here is 3 pi. So if we remember that, that omega is 3 pi, and also we know we have the relationship that omega equals 2 pi over t, where t is the period. So we kind of got to know that. That's important. So if we remember that, then immediately we know that 3 pi is equal to 2 pi over t. That's easy. Then we can just solve for t, and t is 2/3 of a second. So that's the first question. All right. Then we're asked to find the total energy of the system at any point in time. There are a couple ways to do that. One way is probably to just calculate the total potential energy that such a system would have. And we know that a formula for the potential energy would be 1/2 kx squared. Okay, now in order to do that, we can use the value of t that we just calculated in part A to find the value of k, because we know that t equals 2 pi times the square root of m over k. Okay, so this is simple enough. I'm not going to bother going through all the steps because you can see how to do it, but just plug in the 2/3 for t. You're given the mass right here. That's known. That's 1/2 kilogram. So plug in the numbers and move things around, divide by 2 pi, square both sides of the equation, whatever you need to do, and then eventually you can solve for k. Okay, very easy. Once you have k, then just plug that in right here, and you'll have the total energy of the system, with the caveat that you have to use the amplitude for A. So if you want the total energy, then this must be x max right here, x max. And x max is known to be 4 by examination of the original function for the position versus time. So that's one route you can take. I guess the other option is that you can try to take the derivative of the expression up here, and if you do that, you'll have the velocity versus time, and then you can use the formula for kinetic energy with the maximum velocity. And so I'll just do that quickly. So if we differentiate, we're going to find out that v of t is equal to 4 times 3 pi. The chain rule will pull out a factor of 3 pi times the sine of whatever I have inside my parentheses. Same thing I had up there. I'm not going to bother to write it. There'll actually be a negative in front of that because the derivative of the cosine is a negative sine. So we don't really care about what's happening in the oscillatory term here in this piece, because that varies between 1 and -1, and we know we have the maximum velocity when the sine the sine value gives 1. So we're looking at this as our maximum velocity, which, by the way, happens to correspond to omega a. So it can be helpful to remember that the maximum velocity, Vmax, is always equal to omega a. Actually, it's plus or minus omega a, but I don't have room to write that, so I won't. Okay, so then using that v, we can plug it into the formula 1/2 mv squared. We'll have the total energy of the mass. Done. Part C, That's a conceptual question. The idea being that the potential energy, is not just a property of the mass, but it's a property of the mass spring system combined. Technically, the energy is not stored in the mass, but it's stored in the elongation or the compression of the spring. So I'm just getting at that with that question. And finally, what is the displacement of the particle when t is 0.25 seconds? I don't think we need to do that one. Just simply take that value, 0.25 rather, and plug it in for t and calculate what the x value is in the original function. Easy, easy. Let's look at number 2. Also a pretty simple question. So you're given that the amount of work, 3 joules, is needed to compress a spring that distance. So we just use the formula for the potential energy in the spring. PE, or U elastic, U sub E is 1/2 kx squared. So 3 equals 1/2 k, and x is 0.12, which we can't forget to square. All right, so typing those numbers in my calculator, I get 6 divided by 0.12 squared. And that turns out to be, I get a k value from that of 416.7, and that's going to be newtons per meter. Okay, done. So then we have to find the mass. Let's see, probably the easiest way to do that is to work with force. So what I would do in this case, I guess we could take sort of a roundabout approach if we remember that there's a relationship between omega and k and m. But I don't think we need to do that here. I think it's easiest probably just to use the fact that for an oscillatory system like this, the force is proportional to the negative of the displacement. So here, I'll make some room over here. Let's zoom in right here. So we know that F equals negative kx, like that, right? And we just got done finding k. Oops, right up here, right over here. And we found that it was, what, 416.7. So if I plug that in, so F equals negative 416.7, and then I just plug in my 0.12 meters from above. That will give me the force. Well, if I then just divide that by the mass, which they give me, that's the acceleration. And I'm done. So that was fairly easy. Okay, you get the feeling that doing well on these problems involves remembering just lots of little relationships. Let's take a look at number 3. All right, this is key. The speed of the mass is 0 for the first time. So that's going to happen after exactly half a period, when the mass has gotten to the other side, the other extreme point from where it's been released. And so we know the period then is 1 second, since it took half a second to get halfway across. So I'll just jot that down right here. T is 1 second. Sweet. Now the question is, what's the maximum speed of the mass? Okay. Well, so there are probably a few different ways to get this, but the approach I'm going to take is as follows. So we know that the maximum speed, Vmax, is equal to plus or minus omega A. Right, that's a fact. And we have A, we've been given the amplitude, so if we want Vmax, we have to find omega. But again, I use this for the solution in the first question. If we remember that omega is simply 2 pi over t, then the problem is easy. So t is 1, so omega is 2 pi, and the amplitude is, what, 0.1 is what we're told. So then Vmax is simply 2 pi times 0.1. Again, the success with problems in this unit usually boils down to just knowing a bunch of simple equations. Now, if we didn't remember this, there are other ways to get it, of course, but we could try to write the position versus time and then try to differentiate it, but I think doing so would still require you to remember the relationship here, no matter what. So this absolutely is key. Know that. Okay. So for number 4, we have a pendulum that has a known period on Earth, and the question is, what would its period be on the Moon, where the acceleration of gravity is different? So the approach for this, I would suggest you just use the formula for the period of a pendulum, and you find what its length is, and then you take it to the Moon, where the g value is different, and you find what its new period would be there. So I'll just outline that quickly. This is a particularly easy problem. Okay, so it's got the period is, what, 2.5 seconds on Earth, and I know that the formula for the period of a pendulum is t equals 2 pi times the square root of L over g, like that. Okay? So I simply plug in the 2.5 seconds here. I get my 2 pi, square root of L over 9.8. And now I just solve this thing for L, which I'm not going to bother to do because it's very easy. When I get L, I'll get L equals something. All right, now the length of the pendulum is the same no matter where I put it, on the Moon, on the Earth, doesn't matter. So now once I have the value of L, I just do it backwards, and I say, I wonder what the new period is. And that's going to be 2 pi times the square root of L, which I now have, over the new acceleration of gravity on the Moon, which is 1.67. See? And then I calculate my period that way. That's all there is to it. What's interesting about a problem like this is that it kind of shows you that if you have a clock that works based on a pendulum, and many clocks do work on pendulum principles. Old clocks certainly did. If you have ever been to a home, or if you have in your home yourself, one of those big clocks called a grandfather clock, with a big swinging pendulum inside of it, then you know that the swinging of the pendulum is what makes the clock tick. In fact, you probably have to raise a series of weights every couple of days so that you increase the potential energy of them as they fall, which feeds energy back into the swinging pendulum because of friction and resistance and things like that. The pendulum will stop swinging over time. So if you're familiar with one of these clocks, then you get this idea. And the interesting thing about it is if you had such a clock and you brought it to another place in the solar system, like the Moon, it would not keep time correctly because it would swing back and forth either slower or faster depending upon where you brought it. So it's interesting to try to think, what would happen to the time on the clock? Would the clock run fast, meaning it would say it was maybe it's only 12 o'clock right now, let's say 12 noon, but maybe the clock would say that it's 1 o'clock. And so that would be a clock that's running too fast. Or would it be the opposite? Maybe they say the clock would say that it's 11 o'clock when it's really 12. That would be a clock that runs too slow. So think about that for a minute. What would happen if you took this clock from the Earth, where it has a period of 2.5 seconds, and you had a clock based on it, on this pendulum, and you took it to the Moon, kept the same length? What would it say? Would it run slow or would it run fast? That's just a fun thing to think about. Okay, number 5, the last question. So let's see. We have a pendulum, we have the mass, we have the length, and we have the angle through which it's displaced. And the question is to determine its maximum speed and its maximum acceleration and all that good stuff. Okay. Let's find its maximum speed. Let's draw it. So here's my pendulum hanging. If it hangs straight down, then it looks like this. But it doesn't. It's here. You pulled it back. And you pulled it back 15 degrees. That's 15 in there. And so if you want to find the maximum speed, the easiest way to do it is with the conservation of energy. So you got to find the height that it falls through so that you can do something to the effect of mgh equals 1/2. mv squared. The m's cancel, so it doesn't matter. But the challenge is to figure out what h is. H is this little height difference in between here and here, like that. That's not always easy to do for a pendulum. Given the length is L, and of course over here the length is L as well, that's an L, like that, then if you take a few moments and think about it, you can draw a horizontal line from here to here, like that. And if you do that, you should realize that h is equal to L minus L cosine of theta, like so. All right, so if you don't see that immediately, then just spend a few minutes looking at this triangle right here, and that should be apparent. So that's all I need, and I can plug that in for this, and then I'm there, because I just take 2gh, where h is L minus L cosine theta, and I just square root that, and that is my v max, which of course the maximum velocity occurs at the bottom of the swing. Done. Now, the maximum acceleration is a little bit trickier. So I'm going to make some more space here for drawing. So what I want to do is draw this pendulum again. Zoomed in a little bit bigger this time. There's the bob on the bottom of the pendulum, right? And at this moment in time, there are two forces on it. There's this force, mg, like that, and there's maybe this force, which I'm sure is present actually, and I'll call it Ft for tension. I hesitate to call it capital T in this unit because capital T usually stands for period, so I don't want that to be confused, so we'll call it Ft. Now, those are the only two forces acting on the pendulum, and this is the moment of release, when it's the highest. And that actually is the moment when its acceleration will be the greatest. The way we figure out the acceleration is to make a set of coordinates like this, as if we're on an inclined plane. So x and y axes like that. And I think you know how this is going to go. So I'm going to take and break the force of gravity into two components. Yeah, one of them is going to be like this, and one of them is going to be like that. Like so. Okay, now I realize my mg sine theta, or my mg rather, is in the wrong place. So, sorry for that, but really, I'll put an X through that. So this side of the triangle right here, right down there at the bottom, is really mg sine theta, right? We know this from inclined planes because that angle in there is theta. And you can see that because if I put a triangle up here with theta, you could see how these are the same angle. So that's mg sine theta, and of course the other little component we have over here, this one here that I'm on top of right now, is mg cosine theta, but I don't at the moment care about that. I only care about this bit here. Okay. Now the pendulum's not moving yet. I've just begun to release it, so it doesn't have any speed. It's not moving, so there's no centripetal acceleration at this point, meaning there's no acceleration sort of this way in towards the middle like that. It's not present. So the only acceleration that I have is sort of tangential, or in this direction. This is the only acceleration I have at this moment. And it's given entirely, it's caused entirely by this force, mg sine theta, right there. Keep that in mind. That is the only force that acts tangent to the path, this being the path of the pendulum at this moment in time. Okay? So I have a situation here where I have a force that's tangent to the path of the pendulum and is equal to mg sine theta. And you could argue maybe I should do that, right? Because the bigger theta becomes, the more this force points down, backwards, opposite the direction that I'm raising the pendulum. In other words, if I pull the pendulum up to here, so theta is much bigger, then the force is bigger. but points always sort of opposite the direction that I've lifted. I've lifted up like that, and the force is down like that. So hence the minus sign. So this qualifies as a type of a restoring force, but it's not exactly a situation where the force is proportional to the negative of the displacement. It's not like F equals negative kx, like that. And the reason it's not is because we've got this sign in here, kind of messing things up. Right? So it's important to realize that a pendulum swinging back and forth is not really simple harmonic motion, not a true example of simple harmonic motion, and that's why when you did your lab last week, you found that the period of a pendulum was not exactly 2 pi times the square root of L over G, but it had some extra terms thrown in there. The thing is, though, if the angle is small, and by small I mean less than about 15 degrees, then it doesn't really matter. And so what we can say that the sine of an angle is approximately equal to the angle itself for small angles. And I'm doing this with the understanding that theta is in radians, not degrees. So then we can rewrite the force equation above it to be F equals negative mg theta, where we understand this is really just an approximation, not exact. And now we have a situation that fits simple harmonic motion, because again we have a force that's proportional to the negative of the position change. In this case, the position change is being measured by an angle, not by a linear variable like x or y or something like that. Okay? Now there's a little more to the story than that. If we wanted to do this correctly, we should probably be talking in terms of torque instead of in terms of force, and rotational motion instead of linear motion. And we can do that in another unit, but for the time being, this is enough to understand what's going on. So now back to the question that we had before. So the question said, determine its maximum speed. We did that. Determine its maximum acceleration and the maximum restoring force on it. And so you're going to get both of those answers just from an understanding that the force is mg sine theta. So that will be biggest when the angle is as big as it will ever be, which is, in this case, what, I think 15 degrees, which is the angle I release it from. So if you want to know what is the biggest force on the pendulum bob, it's the biggest force is mg times the sine of 15. That's your answer for F max. F max. And if you want to know the biggest acceleration, that's trivial. Just divide that by the mass, and you have your answer. So it's g sine 15. Okay? All right, hopefully these solutions will help as you prepare for the upcoming exam. But again, I would stress that in this unit, maybe more than in previous units, there are lots of little equations to know. So in addition to the x versus t, position versus time equations, velocity versus time, acceleration versus time for an oscillating object, there's also little tricks like this one up here. Omega right here is 2 pi over t. Very helpful thing like that, right? There's also the trick of remembering that the maximum velocity is plus or minus omega a. While we're at it, it's also true that the maximum acceleration, a max, is equal to omega squared a. Again, that's plus or minus. These things can be very handy. And of course, remember the formula for the period of a pendulum and a mass on a spring, because you'll definitely need those. Finally, don't forget that whenever you have something in simple harmonic motion, you have to be able to find a force that's proportional to the negative of the displacement. And I used that idea, it's very small, but I used that idea right here. That's a spring force, but there are many situations that we can construct where you find a force that's directly proportional to the negative of the displacement. It's not just springs that do this, okay? And if that is the case, if you do have a force like that, then definitely you have motion that's simple harmonic. And if you have motion that's simple harmonic, then the acceleration is not constant. Remember that. You cannot use the equations, the constant accelerated kinematics equations that you learned last year. Those are useless to you. But you do know that you have a potential energy that goes by the formula right here in the box, 1/2 kx squared, where k is the spring constant or the elastic constant or whatever people want to call it. All right, that's it. Hope this helps.